9.5, Polar Coordinates and Graphs. While we commonly use the rectangular coordinate system as our graphing tool of choice, we can show that some problems in mathematics are easier to analyze in a polar coordinate system. The Cartesian plane allows us to identify any point in the plane by a set of numbers such as xy or xyz. The equations corresponding to these graphs have been in either rectangular form or parametric form. In polar coordinates, a point in the plane is defined by a pair of numbers r, theta. The number theta measures the angle between the positive x-axis, called the polar axis, and a ray that passes through the point. The number r measures the directed distance from the pole or origin O to the point P. So here is your polar axis, and this would be our theta, distance from this 0, 0 to this point P. That is your r, okay? So for this point P, if this was your point P, your theta is pi over 4. Oops, oh yeah, that's theta. And the distance along that vector is 2. And so you could see that if you dropped a perpendicular here, that you would have an x and a y that corresponded to it. And what you also want to realize is that your r could be thought of as the radius of the circle that is formed by, just taking that and rotating it around the origin. So your 0, 0 is your pole or your origin. So this is your pole, this is your polar axis, and your polar coordinates here, okay? But we'll connect this, you know that your r squared equals x squared plus y squared. Like that's going to be your connection in between the polar coordinates and the Cartesian coordinates, okay? Because you can see right here with this triangle that there's a Pythagorean relationship between this x and this y. So you can either get to this point by going xy, or you can get to it by going theta and then out r, okay? So that's what we're going to be talking about. Now, how are they related? You can think of the graph of the polar equation r equals f of theta as the graph of the parametric equations x equals f of t times cosine t, y of t equals f of t times sine t, where t is theta. So our x, I'm reading it right here, our x is r cosine theta, which would be, if we knew our r in terms of theta, then it would be f of theta times cosine theta, and our y is r sine theta, which would be, if we knew r in terms of theta, it would be f of theta sine theta. So in this lesson and the next, we will explore the polar coordinate system, conversions of equations, graphs, and focus on tangent lines, arc length, and area. Those are the things we're going to focus on. So a quick crash course for the polar coordinates. So the polar coordinates r, theta are related to the rectangular coordinates xy as follows. If given r, theta, then x equals r cosine theta, y equals r sine theta. Now let's think about this for our unit circle. When we used to talk about our unit circle, and we would always give the points 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Remember how we used to say that this is, since this is 0, this is like, the cosine of 0, comma, the sine of 0. And this one is the cosine of pi over 2, comma, the sine of pi over 2. And this one is the cosine of pi, comma, the sine of pi. Well, remember, this is the unit circle, and our radius is 1. So if our radius is 1, this is like 1 cosine theta, 1 sine theta. 1 cosine pi over 2, 1 sine pi over 2. So what I'm trying to have you understand is that your x value is r cosine theta and your y value is r sine theta. So that's going to be true if we, just like that point we just had, pi over 4 and then go out 2. And so this x is going to be 2 cosine pi over 4, and this y is going to be 2 sine of pi over 4. Okay, if we were, if we had graphed that polar coordinate 2 comma pi over 4, okay, that would have been this point, and we could have looked at it as 2 cosine pi over 4 comma 2 sine pi over 4. And then rectangular to polar, if given xy, then r squared equals x squared plus y squared. We also have, if this is our x and this is our y, we can see that opposite over adjacent would be the tangent of theta is y over x. So we also have that situation. So either r squared equals x squared plus y squared, or the tangent of theta equals y over x. And now we go to converting the following polar coordinates to rectangular coordinates. So this is our polar coordinate, this is our r, this is our theta. And so the first thing we're going to do is we're going to say that our x equals r cosine theta. And when you think about your 2 pi over 3, remember, go to 2 pi over 3, 60-degree reference angle. So this is square root of 3, negative 1 and 2. So if I wanted to find 4 and then find the cosine, it'd be negative 1/2. So my x value is negative 2. And then we'll do the same thing with y. We take our r, and then we do the sine of 2 pi over 3. So y equals 4 times, and this is going to be square root of 3 over 2. And so our y value is 2 root 3. So if we were going to convert 4 comma 2 square root of 3 into xy point, it is equivalent to negative 2 comma 2 root 3. And so if we went to 2 root 3 and went out 4, this is the same thing as negative 2 and 2 root 3 here. That's how you get to the same point P here. You're just finding a way to say, I want to talk about this point right here in space. Okay, our next one, r comma theta. Again, we have our x equal to our r times the cosine of pi over 6. And so for pi over 6, we know that's a 30-degree angle. This is a 1, square root of 3 and 2. So this becomes the square root of 5 times our cosine would be square root of 3 over 2. And so that gives me square root of 15 over 2. And then our y value would be square root of 5 times the sine of pi over 6, square root of 5 times 1/2. So that's square root of 5 over 2. So our xy coordinate, square root of 15 over 2, comma, square root of 5 over 2. That is what this is equal to. Just like we found this one over here. I didn't circle it. Okay, now on example number 2, let's convert the rectangular points to polar points. So these are rectangular, so I know that these are at xy points because it told us. They are rectangular points, and we're going to put them in form. We want them to go into the form of r comma theta points. And so we know that r is equivalent to the square root of our x squared plus our y squared. So that's going to be the square root of 4 plus, and then I square the 2, I get 4. I square the square root of 3, I get 3. So this gives me the square root of 12 plus 4, which is the square root of 16, which is 4. And then to find our theta, we know that theta is the inverse tangent of y over x. And that gives us the inverse tangent of negative square root of 3. Now for inverse tangent, I'm gonna tell you that typically inverse tangent, we have to go, if it's positive, we go to the first. If it's negative, we go to the fourth. And so typically I would be going this way, and I would be looking for the opposite over the hypotenuse, over the adjacent, opposite over adjacent. So this would be a 2, and this would be a negative 60-degree angle. So our theta would be equivalent to negative, what would this be? Negative pi over 3, sorry. But they didn't tell us, but I think they're wanting us to give them a positive form of that. So the positive form of that, we would just look at this right here, and we would give an answer 2 pi over 3. So this would still be a 60-degree. This would be square root of 3. This would be a negative 1. So in both of these spots, your answer to the tangent is negative square root of 3. If you did not want a negative angle, your theta would be positive 2 root 3, but I'm going to tell you that typically when you're solving an inverse tangent problem, if it's positive, you go to the first. If it's negative, you go to the fourth. But they have an answer of 4 comma 2 root 3. I think they just wanted to keep it positive. Inverse tangent has infinitely many answers unless you narrow down the spot that it's in. So they probably just wanted theta between 0 and pi, or 0 and 2 pi. All right, so that was our first one. Next one, r equals square root of 5 squared plus negative 5 squared. Square root of 25 plus 25. Square root of 50, which is the square root of 25 times the square root of 2. So our r is 5 root 2. Our theta would be inverse tangent. Oh, actually, I know why this was the way it was. Because look, if I went to the xy, I would go negative 2, positive 2 root 3, or 2 square root of 3. And so I was in the second quadrant. That's why we should throw that out. I'm sorry. I just remembered that's why we did that, because we're in the second quadrant. Anyway, so now for this one, we are positive, negative. Now we're in the fourth quadrant, right? Because we're going to positive 5, negative 5. So we're trying to find the polar coordinate for this point P. And so this would be our y over x. So we're finding the inverse tangent of negative 1. We know that is negative pi over 4, right? So our theta is negative pi over 4. And so this would be the point, the r comma theta point of 5 root 2 comma negative pi over 4. I might write it down here. I feel like that was just... Okay, so there's your answer for letter D. All right, just like converting points from one system to another, we can also convert equations. So example number 3, convert the rectangular equations to a polar equation and then verify with your calculator. This is kind of cool because these polar equations that typically do not look like, they look like they'd be complicated. They end up being just pretty easy functions. So the first thing we need to remember is that our x is r cosine theta and our y is r sine theta.
If there is a custodian with a radio, can you please call the main office?
Since we have y equals 4, we're going to put r sine theta in for y, and we're going to see that r sine theta equals 4. Well, if I wanted to solve for r, I would be dividing by the sine of theta on both sides, and we would write this instead of 1 over sine, we would write it as, cosecant. So this would be 4 cosecant theta. And what we could do now, I'm going to go over to my, my graphing calculator. And I was thinking, there we go, that I'm going to pull up a polar coordinate. Look at that polar coordinate. See how it puts us into, you can do this with your TI-84 also. And we're going to put in 4 cosecant. Let's see, if I hold down on this, I think it gives me cosecant. 4 cosecant theta. And I think if I hold down, it might give me theta. Nope. One of these is going to give me theta. That was it. Oh, sorry. There we go. Okay. And let's hit enter. Look at what it gives us. 4 cosecant theta in polar coordinates gives us y equals 4. So this is the line y equals 4. And so I thought that was so cool that, you know, we're changing this y equals 4 into polar coordinates, and the graph of this is just this line, right? So very cool. So now for this one, our y is r sine theta equals 3 r cosine theta plus 2. And so we've got our r sine theta, and I'm going to move this minus 3 r cosine theta equals 2. I wanted to move those over. Now I'm going to factor the r out. Sine theta minus 3 cosine theta equals 2. And then I'm going to solve for r. So r is 2 divided by sine theta minus 3 cosine theta. And so this is your polar equivalency to y equals 3x plus 2. So let's go back and try and put that in. 2 over sine theta minus 3 cosine theta. So in my TI Inspire, I can't remember how to pull that graph up. Oops. Nope. Sorry. Cancel. Here we go. And I think if I just go up arrow, I can take this one out, and I can put in a fraction. There we go. So 2 down arrow, and this will be sine. This is kind of hard to use. Sine theta. Close my parenthesis. Minus 3 cosine theta. I'm going to hold it and go up. There we go. And look at this. It goes through, back. darn it. It goes through at positive 2, and it has a slope of 1, 2, 3, 1. So this is the line y equals 3x plus 2. But in polar coordinates, it looks like 2 over sine theta minus 3 cosine theta. I think that's so cool. Let's look at C. So our r sine theta equals 2 r cosine theta squared. And so r sine theta equals 2r squared cosine squared theta. So we're going to divide by r on both sides. This one goes away. Sine theta equals 2r, right? Because one of those goes away. 2r cosine squared theta. And then we solve for r. So we're going to be dividing by 2 cosine squared theta on both sides. So our r is equal to 2 sine theta over 2 cosine squared theta. Now, you could also write this, because you could write it as sine over cosine times 1 over cosine, and then still have your 1/2 out here. That still is going to be sine theta over 2 cosine squared theta, but we could write it with a tangent and with a secant. So this could be 1/2. Where do I write that? I guess I'll just write it down here. This could be 1/2 tangent theta secant theta is your r. I guess I'll write it up here. R equals 1/2 tangent theta secant theta. And if we graphed it, it would look like a parabola y equals 2x squared. Pretty cool. Okay, convert the polar equations to rectangular, then verify with your calculator. So for this one, r divided by secant theta is -3. And so what we can do here, you're trying to produce either r cosine theta or r sine theta. And if we moved the secant into cosine over 1, right, because it's 1 over secant, so that's cosine over 1, you can see that r cosine theta is going to be your x value. So this is the same thing as the vertical line, x equals -3. If we put r equals -3 secant theta into our calculator, it's going to graph this vertical line that goes through -3. And then this one, if we multiply by 1 plus 2 cosine theta on both sides, so r times 1 plus 2 cosine theta equals 4. R plus 2r cosine theta equals 4. R plus 2, and then r cosine theta is x equals 4. And then what you want to do with this r is you want to put in the square root of x squared plus y squared. Oops. And then I'm going to move my 2x over. Okay, I was going to do it on the next step, but we might as well do it this time. Now you want to get that square root out of here, so you're going to take the square of both sides. Square root and the square go away over here, so I'm left with x squared plus y squared. This one becomes 16 minus 16x plus 4x squared. And now let's set this equal to 0 and get everything over to this side. We've got now, if I subtract x squared, I'll end up with 3x squared. If I subtract y squared, I've got minus y squared. Then I've got my negative 16x and my positive 16 that stay on that side. So this is my rectangular or Cartesian coordinate for this right here. Do you want to see what that looks like? I kind of am curious. So let's go to our TI Inspire. Go to our polar coordinates. I'm going to go up and take that one out so it doesn't confuse us. And we are going to put in another fraction. This time we're going to have 4 on the top. And 1 plus 2 cosine theta. Look at that. Now, this is just a hyperbola. The x here that you see, that really isn't part of the graph. That is just what it approaches. Those are those slant asymptotes that it approaches, so ignore that x. But the part on the side, the curved part, that is the actual function. And if you go back and look at the, it's a positive x squared and a negative y squared. So we knew that it wasn't going to be along the y-axis, it was going to be along the x-axis. And so if we would have, combined these x's and completed the square, we would have seen how it shifted over, the center of it was shifted. But that was cool. All right, now part C. We're going to multiply by the denominator on both sides. And distribute the r. R cosine theta is x, and r sine theta is y. So that gives us x plus 2y equals 3. If we would solve that for y, it would be linear, okay? So that would just be a line if we went and looked on our calculator. Example number 5, describe what you know about the graph of each polar equation. Then convert the polar equation to a rectangular equation and sketch the curve on the grid provided. And so, what do I know about r equals 3? Well, I know that r is the square root of x squared plus y squared. And so that equals 3. If I squared both sides, this would give me x squared plus y squared equals 9. This looks like the equation of a circle. So I think that this is a circle centered at 0, 0 with a radius of 3. So this is a circle centered at 0, 0 with a radius of 3. So if I graph this, circle centered at 0, 0 with a radius of 3. Now, think about what the polar coordinate was. R equals 3. So here, it's 3. It's 3. It's 3. It's 3. It's 3 for everything, right? So you should have known then that was, that was what it was. It was just creating that circle for all of those thetas. And I really don't like it when it has that stuff on the inside. But anyway, there it is. All right. B. R equals negative 3 sine theta. Okay, well, let's think about this. If we multiply by r on both sides, we get r squared equals negative 3r sine theta. And so we know our r squared is x squared plus y squared. And we know that r sine theta is y. So there is our rectangular coordinate. Now, I'm thinking this looks like a circle. And what we would do to find out like how to draw this, we would bring that 3y over, leave a space. This is going to equal 0, but I'm going to leave a space. We're going to take that 3, divide it by 2 and square it. 9/4. So I'm adding 9/4 here. I'm adding 9/4 here. X squared plus, we've just completed the square. And now what we should see, this is has a center 0, negative 3/2, has a radius of 3/2. Because remember, this is like the radius squared. And so if I was going to take square root, oops, I put a little dot there. If I was going to take square root to find what my radius is, it would be 3/2. So if we're centering it at 0, negative 1.5, that's about right there is our center, and it has a radius of 1.5, so I'd go out 1.5 here and 1.5 here. It's hard to draw it perfectly, but it's going to be something like that. And of course, this would, these would be lines because there'd be so many points it would look like a line. But that looks like that. That is your equation. And then r equals 5 over cosine. What do you think we would do with that? Multiply by cosine, you think? And then r cosine theta is x. So this is going to be a vertical line going through 5. So that is what this is. If I put it into polar coordinates, it's also what this is. Okay? All right. Using auxiliary graphs to sketch polar coordinates, or polar curves. Consider the function. Now we're going to use an auxiliary graph, okay? This is going to sound weird. It's going to look weird, but consider this function from 0 to 2 pi. Shown at the right, okay? So they've already sketched it. And its relationship to the polar graph. Notice that we just changed the r to a y, or the y to an r, and the x to theta, okay? So since there will be unique y values on this domain, we can use the table below to assist in graphing the polar graph. So if we put 0 into our y equals, so this one is for our y equals 1 minus 2 sine of x. If I put 0 in, the sine of 0 is 0, so that just leaves me with 1. If I put pi over 6 in, the sine of pi over 6 is 1/2, and the 2's would cancel and I'd get 0. If I put pi over 4 in, da-da-da-da-da, okay? And it even wraps around, and it goes from 0 all the way, it wraps around and continues all the way to 2 pi. And so what they're saying is that if we wanted to look, since our y was going for r and our x for theta, then y comma x is going to coincide with r comma theta. And what does this mean? Well, if you start graphing all of these r comma thetas, so the first one you would graph is 1, 0, okay? And then you would graph pi over 0 pi over 6. So 0, and then go 0 at pi over 6. Well, that means you're going nothing anywhere. But the minute, I want you to focus on the minute that this right here, all of these values are negative, when your theta values are all positive. Okay, so here's your theta values are all positive and have negative R values. That is where your inner loop is going to occur. So I'm just going to write this negative R values create the inner loop. Okay, because they're going to be where you would go, how shall I say that? You're going pi over 4, but then you're going backwards the negative 4.1. So that where you normally would go to here and then go this way up 0.41, you're now going to go this way 0.41, okay, because you go backwards.